In this video, we'll understand the basics of transformers and attention mechanisms in a simple step-by-step way. We'll see why attention became such a big breakthrough, how transformers process sequences, and why they often perform better than older recurrent models. Along the way, you'll also get quick quizzes to test your understanding. Attention mechanisms changed deep learning by allowing models to focus on the most relevant parts of the input instead of treating every part equally. This is especially useful in tasks like language understanding and image recognition, where context matters a lot. In simple words, attention helps the model decide what deserves more importance at each step. Transformers are special because they rely on self-attention rather than sequential recurrence. That means they can connect words or tokens that are far apart in a sequence and still understand their relationship well. Also, unlike RNNs, transformers process the full sequence in parallel, which makes training much faster and more efficient. The traditional encoder-decoder model converts the input into a context vector and passes that summary to the decoder. This works, but with long or information-heavy sequences, a single fixed summary can become a bottleneck. Also, during generation, not every part of the input is equally important. That limitation is one big reason attention became so important. Now, let us look at this in a simple table format.
Transformer vs RNN, LSTM.
Main differences in sequence modeling. Here is the main comparison to remember. Transformers use self-attention and process tokens in parallel, while RNNs and LSTMs work step by step. Because of this, transformers usually handle long-range dependencies better and train faster on modern hardware. This is one of the biggest reasons they became the dominant architecture for sequence tasks. At a high level, the transformer architecture has an encoder and a decoder. The encoder reads the input and builds rich representations. The decoder uses those representations to generate the output sequence. Inside these blocks, we find attention layers, feed-forward networks, normalization, and residual connections working together to make learning stable and powerful. Now that we've covered attention basics, let's test what we've learned so far.
Here's quiz number 1. See if you can get it right.
Question 1. What is the main role of attention in deep learning models? The correct answer is to focus on relevant input paths. Attention helps the model assign more importance to the most useful parts of the input. Question 2. Why are transformers generally faster to train than RNNs? The correct answer is they process sequences in parallel. Transformers can handle the full sequence at once, unlike RNNs which process step by step. Question 3. What is a key limitation of the basic encoder-decoder model mentioned in the article? The correct answer is it depends on a fixed summary vector. A single context vector can struggle to preserve all relevant information for long input sequences. Self-attention works by creating 3 vectors for each token: query, key, and value. A token's query is compared with other tokens, keys to produce attention scores. After normalization using softmax, those scores are used to combine value vectors. The final result is a context-aware representation where each token gets information from other relevant tokens in the sequence. The real strength of self-attention is that it does not struggle just because 2 related words are far apart. It can directly connect them. So if a sentence has a pronoun like Kate, the model can better figure out what that pronoun refers to by looking across the full sequence. This makes contextual understanding much stronger. Multi-head attention means the model runs several attention operations in parallel. Each head can focus on a different kind of relationship in the input. One head may capture grammar, another may capture semantic meaning, and another may focus on positional patterns. When these are combined, the model gets a richer and more nuanced understanding of the sequence. After attention, transformers use feed-forward neural networks to refine the representation of each token. These networks typically apply 2 linear transformations with a non-linear activation, like ReLU, in between. Attention captures relationships across tokens, while the feed-forward network strengthens the representation at each position independently. Now that we've covered core components, Let's test what we've learned so far.
Here's quiz number 2. See if you can get it right.
Question 1. Which three vectors are used in self-attention? The correct answer is query, key, value. Self-attention computes query, key, and value vectors for each input token. Question 2. What is the main purpose of multi-head attention? The correct answer is to capture different relationships in parallel. Different heads can focus on different aspects of the input, making the representation richer. Question 3. What do feed-forward networks mainly do inside transformers? The correct answer is refined token representations. FFNNs process each position independently after attention to improve the token representation. One important point is that transformer architecture is flexible. Some models are encoder-only, some are decoder-only, and some use the full encoder-decoder setup. The right design depends on the task. For example, understanding tasks may use encoder-heavy designs, while generation tasks often rely on decoder-based models. Transformers are now used across many domains. In natural language processing, they power translation, summarization, and question answering. In computer vision, they help with image understanding as well. Overall, transformers have become a foundation for many state-of-the-art AI systems because they combine context awareness, flexibility, and strong performance. Now that we've covered applications recap, let's test what we've learned so far.
Here's quiz number 3. See if you can get it right.
Question 1. Which transformer variant is commonly suitable for generation tasks? The correct answer is decoder only. Decoder-based transformer designs are widely used for sequence generation tasks. Question 2. What helps transformers capture long-range dependencies? The correct answer is self-attention. Self-attention allows tokens to directly relate to other relevant tokens across the sequence. Question 3. Which field besides NLP is mentioned as an application area for transformers? The correct answer is computer vision. The article specifically mentions computer vision as another important area where transformers are used. That's the core idea of transformers and attention mechanisms. If you understood why attention matters, how self-attention works, and why transformers are faster and more effective than older sequential models, then you've got a strong foundation. Keep learning, and next time we can go even deeper into positional encoding, masking, and real model examples.